Hello and welcome to CS 500 Design and Analysis of Algorithms. My name is Martin Ziegler and I'm delighted to be your instructor for this course over the next weeks and months. This is a graduate level course, so the prerequisites include, for example, introduction to algorithms and discrete mathematics. We're going to use mathematics a lot in this course, so please be prepared and make sure that you have the appropriate background. In this course, we're going to have a new and I'm going to say particular or even peculiar perspective on algorithms, namely the focus on different ways of analyzing algorithms, how to assess the quality of an algorithm, how to predict the performance of an algorithm in various ways, and then depending on how what emphasis we want to stress about an algorithm, then design or redesign an algorithm to do better on that particular category. Let me show you the slides and explain what I mean with that. So design and analysis of algorithms means that we're going to take a look at various notions of performance of an algorithm, and we're going to analyze the algorithm using various modes. For notions of performance, cost measures is one important keyword, and modes of analysis is the other important keyword. Let me expand on that. So what are typical and new modes of analysis that we're going to consider in this course? First, there's the classical setting. That's the worst case mode of analysis. They're all familiar with that. For example, quicksort is well known and famous for having running time n log n, but actually in the worst case, it has quadratic running time n squared, as bad as bubble sort. A more realistic, arguably more realistic mode of analysis is the average case. Here, quicksort has average case behavior of n log n, thus formalizing and explaining for its practical perceived high efficiency. That's a second mode of analysis. Then we're going to analyze algorithms in the expected case pertaining to randomized algorithms, in the amortized sense pertaining to a repeated execution of some algorithm, of some method in a data type. We're going to analyze algorithms with respect to their competitive ratio that pertains to online algorithms, with respect to their approximation ratio that applies to approximation algorithm. And there are many more modes of analyzing an algorithm's performance. Now, that's one aspect, mode of analysis, and the other aspect, as you remember, is cost measure, notions of formalizing performance. Again, the traditional, the classical way is running time here meaning sequential running time, because of course there are also parallel running time that applies to parallel algorithm, which we'll also study in this course. Then sometimes the real limitation is not the running time, but the memory use. So we're going to dedicate an entire chapter to studying many memory efficient algorithms and analyzing memory efficiency of algorithms. Then when talking about parallel algorithms, the question comes up, how many processors does such a parallel algorithm use in order to achieve its purported performance? Or on a lower level, when we talk about circuits, how many gates does the circuit use in order to process some data in parallel? Also applying to parallel algorithm is the communication volume, which actually we won't address in this course, but this is to give you an impression that there are so many different measures of algorithmic cost and different modes of algorithm analysis. And the design of analysis naturally follows the target, which cost measure and which mode of analysis we're actually interested in. And the purpose of algorithm analysis is, generally speaking, to predict the behavior of an algorithm before and without having to actually execute the algorithm. Executing an algorithm before actually implementing it, being able to choose which algorithm to implement after having analyzed different algorithms. Also, an algorithm, when executed in practice, that execution only applies to one particular input, or in case of randomized algorithm, to one particular sequence of internal coin flips. So getting a thorough picture of an algorithm's performance is not possible by means of empirical execution only. Even thorough benchmark suites only provide a limited view on an algorithm performance, whereas analysis of algorithms takes into account all possible inputs, takes into account all possible internal bit flips. So the goal here is to get a prediction of the behavior of an algorithm independent of hardware details. So, for example, independence of the clock rate. If the same algorithm is implemented and run on a different computer, naturally it will behave differently. But the analysis of algorithms is a larger perspective that pertains and is independent of such particular details of hardware. The goal, of course, is to have this prediction to be as realistic as possible on the one hand, and on the other hand, as simple as possible. And that's a kind of a dilemma, because the simple analysis may not be the most realistic ones, and the most realistic ones might be very involved. So I'm going to say more about that in a minute. But one final purpose of algorithm analysis is to give an impression about whether the algorithm admits improvement possibility or not. So that's a question of optimality of an algorithm with respect to the various cost measures, with respect to the various modes of algorithm analysis. But as I said, between realistic predictions and simple prediction, there's a trade-off. For example, one can say and prove that an algorithm is polynomial, but better impression is given by conveying the degree of the polynomial. Is it a cubic or is it a linear time algorithm? That's all polynomial. And even within cubic or linear time, even more refined analysis may exhibit the constant factors that we ignore for simplicity in the big O notation, but refined analysis can also exhibit that. So here we have a trade-off between realism and simplicity, and that also applies into the cost measures. For example, a cost measure could simply count the number of operations executed by the algorithm, or a more realistic but also more involved analysis could count the number of bit flips performed by the algorithm. And even more involved could take into account memory hierarchy latency issues, like does the algorithm operate on CPU registers, on level 1 cache, level 2 cache, on random access, or on external memory. So these are all various ways to take into account, possibly take into account when analyzing algorithms for the purpose of predicting their behavior. So with that motivation covered, let's now dive into the summary and the overview of this course. So first, we'll give a brief introduction to theoretical computer science and the virtues. And then we'll talk and maybe recall some basic and some advanced 3 data structures that we're going to analyze, and which we're going to design and analyze algorithms for and on top of. Then we'll talk about average case analysis as a way of refining the traditional worst case analysis. We will talk about amortized analysis, about expected case analysis with randomized algorithms, about competitive analysis for online algorithms. Then we'll have a brief intermission about P versus NP complexity theory that leads us to study approximation algorithms for NP-hard problems, where we're going to analyze the approximation ratio. Then we'll talk about parallel algorithms, where the goal is to minimize the parallel running time. And finally, we're going to talk about memory-efficient algorithms. So 10 entire chapters in this course, and each chapter actually is only an appetizer, a door opener that should make you interested in the area of research that is actually going on behind each of these topics. Is the full-fledged research direction that can lead to entire PhD projects. But this is beyond the purpose of this course. The course here is supposed to make you interested and to open the door for you to maybe look further into selected of these 10 chapters. So let's have a look into the syllabus of each chapter individually. First chapter is introduction and recap. Here we will recall what I call the virtues of computer science, the aspects in which that distinguish computer science from, let's say, electrical engineering. I'm going to emphasize the power of abstraction, the many layers of abstraction that nowadays computers build on and that are hidden and thus make them tractable, motivating and emphasize the importance of asymptotic as opposed to absolute efficiency, absolute running time versus asymptotic growth, recalling some classes of asymptotic growth, and then we'll recall the classical sorting problem and emphasize two aspects of the virtues of computer science, namely specifying a problem and proof of optimality at the example of sorting. That's chapter 1. In chapter 2, as you recall, we'll consider some data structures, data types, particularly trees data structures. We start with abstract data types, emphasizing, illustrating the importance of abstraction, which hide hardware and implementation details. Then we'll briefly recall basic data types and derived data types, in particular linked data types and linked data structures, such as trees. And here we're going to expand on AVL trees, their definition, what is an AVL tree, and their properties, the depth and size relation. And we'll talk about algorithms on AVL trees, ways of implementing the operations on AVL trees, maintaining the AVL property, the algorithmic cost of these operations, and the deficiency of AVL tree that motivates us to then look into binomial trees and binomial heaps. Definition of binomial trees and binomial heaps, operations on binomial tree and binomial heaps, and analysis of algorithms that operate on binomial heaps, in particular extract bin operation, decrease key operation, and the merge operation, all in worst case logarithmic running time. Now, having covered the worst case, then in chapter 3, we'll proceed into average case analysis. Recall the purpose and modes of algorithm analysis, and we motivate average case analysis with a toy example, namely incrementing a binary counter. And we'll recall, or maybe teach you newly, the analysis of quicksort, the naive quicksort with the naive pivot choice, not the advanced choice with using the linear time median. And we're going to prove that in average case, indeed, this naive quicksort has n log n running time as opposed to the worst case quadratic running time. And we'll talk about the simplex algorithm for linear programming and its analysis in the worst case and in the smoothed case. So that concludes chapter 3. In chapter 4, we'll talk about amortized analysis. So we talk about bit cost, again considering the binary counter, but this time from the perspective of amortized analysis. We're going to emphasize the similarities and differences between amortized and average and actually expected case analysis. And we'll introduce a new data structure, Fibonacci heap, which is a kind of variant to binomial heaps, define what is a relaxed binomial tree, and the operations extract min and decrease key when implemented on a Fibonacci heap. Then we'll analyze the Fibonacci heap in the amortized setting, and then we'll discuss their applications to the computation of minimum spanning trees, accelerating classical algorithms like prim algorithm from using a binomial heap versus using this newly developed Fibonacci heap and its amortized analysis. Similarly, we're going to recall Kruskal's algorithm also for computing a minimum spanning tree and its implementation building on top of a union disjoint set data structure, namely the union find data type. So I'm going to tell you what are disjoint set data type, what operations they support. We talk about fast and slowly growing function because then we're going to analyze a different implementation of a disjoint set data structure and see that their amortized cost is a very slow growing function. First, we're going to analyze the union by weight heuristic, and then we're going to analyze the lazy union by rank with paths compression heuristic, which turns out to grow as slowly in amortized cost as the inverse Ackermann function. So that's our long chapter 4 in amortized analysis. Then we proceed from amortized analysis to expected case analysis, namely to randomized algorithm. And we're going to motivate that by arguing that randomization, although might create some errors in algorithm execution, actually the reliability can be superior to the purportedly deterministic algorithm. We'll discuss sources of randomness, sources of coin flips, fair and biased coin flips. We're going to distinguish between Las Vegas algorithms and Monte Carlo algorithms. We're going to discuss the problem of primality testing, devising and analyzing a famous randomized algorithm for primality testing whether given integers a prime number or not. We're going to review errors, one-sided errors and two-sided errors of randomized algorithm and how to reduce these errors, how to amplify the reliability of such randomized algorithms. And we're going to apply that to a black box polynomial test algorithm using the Schwarz-Zippel lemma from probability theory. And then we're going to apply that black box polynomial test to devise and analyze a very elegant algorithm for testing whether a given graph admits a perfect matching, namely by exhibiting and harnessing its relation to the TUT matrix and TUT determinant. That's chapter 5. And in chapter 6, we're going to proceed to competitive analysis. That's a way of analyzing online algorithms. And we're going to motivate online algorithms and analysis with a ski rental problem. And we'll discuss the break-even algorithm for ski rental. And in particular, we're going to show that it is too competitive and that too competitiveness is best possible for the deterministic algorithms solving the ski rental problem. So this is going to be an optimal algorithm. It cannot be improved, at least not deterministically. And we're going to talk about another online problem, named the paging problem. And we're going to analyze the least recently used strategy and show that it is k-competitive, where k denotes the number of cache pages, the size of the cache. And we're going to also analyze the least frequently used strategy and show that this is not competitive at all. It has no bounded competitive ratio. So least recently used, we're going to show k-competitiveness is optimal, at least deterministically, among randomized online algorithms. Expected competitiveness can be even better. Namely, we're going to design and analyze a randomized online algorithm for the ski rental problem, which is 1.84 competitive. That is, it beats the optimal 2 competitiveness for deterministic algorithm. That's chapter 6, competitive analysis for online algorithm. And then we're heading for chapter 8 about approximation algorithm. But to understand the importance of approximation algorithm for NP-hard optimization problem, chapter 7 gives a brief recap about complexity theory, about the classes P and NP. It discusses some decision and some optimization problems, particularly the decision problems on graphs, whether it has a Eulerian or Hamiltonian cycle, decision problems on graph about edge and vertex cover, click, and independent set as decision problems for graphs. We're going to recall polynomial time reduction as a means of comparing decision problems of unknown complexity. And then we'll proceed to two optimization problems that are NP hard in a certain sense, namely the traveling salesperson problem and the knapsack problem. And since these are hard, we cannot expect to solve them exactly to find the optimal traveling salesperson tour or the optimal knapsack content exactly. Instead, we're going to analyze approximation algorithm for these problems, namely for the metric traveling salesperson problems. Christofides' algorithm achieves approximation ratio 2. And for the knapsack problem, one can even find fully polynomial time approximation schemes by modifying strongly polynomial time algorithm using dynamic programming to obtain a fully polynomial time approximation scheme. On the other hand, some problems cannot be approximated at all, and that includes the non-metric traveling salesperson problem. So that's chapter 8 about approximation algorithm and their analysis. And we're almost towards the end. In chapter 9, we'll talk about parallel algorithms and parallel runtime analysis. We're going to classify parallel algorithms depending on modes of communication and shared memory. We'll discuss the parallel prefix algorithm for efficiently computing sums over some, or abstract sums over some associative operation. We'll apply that to devise and analyze the carry look-ahead adder for fast addition of long binary integers. We discuss parallel matrix algorithms, and we discuss sorting networks, in particular Bitonic sorter. That's a parallel algorithm. And finally, we talk about memory efficient algorithms, motivating the importance of memory saving. And we'll revisit our different algorithms for computing Fibonacci numbers now from the perspective of how much memory they use. We'll devise an algorithm for concise Boolean matrix powering that is very memory efficient, and apply that to the graph reachability problem, comparing its memory use to the classical Dijkstra's algorithms memory use. We observe that saving memory can become costly in terms of running time. And on the other hand, we devise methods, general methods for saving memory. We see that memory efficiency is surprisingly closely connected to efficient parallelizability. We did talk about streaming algorithms, and we talk about algorithms that use and are aware of the memory hierarchy. So that's all 10 chapters of this course. And the pedagogical philosophy behind that is uses two aspects. One is quote from Konrad Lorenz, got the Nobel Prize in 1973, who observed that what is taught is not said, what is said is not heard, what is heard is not understood, what is understood is not believed, and what is believed is not yet advocated, what is advocated is not yet acted on, and what is acted on is not yet completed. So in other words, there are so many obstacles on teaching, from what the teacher might think to what the teacher says, what the students understand, believe, advocated, and so on, and will make deliberate efforts to overcome all these possible obstacles to learning. For example, we are going to conduct surprise mini quizzes during some of the lectures. We have assignments, homework assignments, where you're asked to apply or to reanalyze and to redevise algorithms by yourself. And we have programming assignments where you're be asked to implement algorithms that we have devised and analyzed in order to really cover all these large stairs from what is thought to what is completed. And speaking of stairs, another important lesson from pedagogy is Bloom's hierarchy of cognitive learning, where knowledge is an important foundation, but the hierarchy extends far beyond and higher to that, and we're making particular effort to climb beyond knowledge. Knowledge is something that a memory stick can do very well, but your capability is more specific, and we're going to use the assignments to raise you to comprehension, application, analysis, synthesis, and evaluation. So that's our plan. Thank you very much for your interest and attention, and I look forward to teach you all the following 10 chapters. Thank you very much.